right. Okay. So before we get into this demo, I'd like to set a little bit of the context of what we are trying to do and what we're trying to achieve, and then we can talk more about the solution in detail. So what we see here is a diagram. You see that basically the solution is developed in two phases. We have a company that has power plants, for example, and that's scattered across the country. And its headquarters, the corporate headquarters, is based off a city where the central data science team sits. So what's really happening here is you can see that there are sensors and these multiple sites and these multiple plants. They are all being continuously, this is time series data that's been fed, that's been stored, and all of this is now being centrally accessible to the team that sits out of the corporate headquarters. So first of all, to start off with, what is our problem? We're really trying to detect anomalies in a power manufacturing plant equipment. While detecting anomalies is just the first part, we really want to then dig a level deeper to identify the key driving factors and finally determine what's the root cause of these anomalies that we detected. We end this with, we also look at different data sources. We have the sensor data. We also analyze the log files, as there's a lot of important information in the log files, and we collate that to come up with one final recommended action that needs to be taken. So as I said, the solution is developed in two phases, and one of the phases really involves utilizing the containerized services from Microsoft. So why do we really require containerized services? The first thing, it really provides the engineers to detect anomalies by deploying AI or machine learning on the edge or locally. It's also particularly beneficial where internet connectivity is unavailable or not so stable, let's say that. Fully disconnected containers also provide greater flexibility for the on-site engineer to have greater control over data and data security and privacy concerns. And last but not the least, on-premise deployments of the containers also provide higher throughput of the data. So let's just talk a little bit about how TIBCO and Microsoft came together to build this really impressive solution. And we were using the Microsoft Anomaly, we were using the Microsoft Azure ML anomaly detection routine. And this is used in our first phase, which I'll go into detail, where we detect anomalies on historic data from all the sites. Let's say if you have 10 sites, so we're looking at data from all 10 of them. Then in the phase two, we are utilizing containerized cognitive services for both detecting anomalies and also analyzing the logs at the edge or at a specific site location. And all of this is also done with seamless integration into the two platforms that we're talking about. One is TIBCO Data Science, and TIBCO Data Science with Azure ML. It integrates at-scale data science operations with various Microsoft Azure ML services. It also enables data science-backed visual analysis using TIBCO Spotfire. And in the second phase for the equipment maintenance dashboard that we've built, it basically adds a root cause analysis for the anomaly detection containerized service. It also recommends actions from TIBCO Analytics with an input from the Microsoft's AI services. In this case, it's the key phrase extraction. And if there are no questions at this point, we can dwell a little deeper into what the architecture looks like. So, and this is where I was talking. Two phases. This is the first phase where we use TIBCO Data Science Platform to analyze data at scale. And here we're calling out to the Azure ML anomaly detection routine. And once we have detected anomalies on all the sites, now this serves as an artifact for the analyst or the maintenance engineer who would eventually then go on to a local site when called upon. And what happens here is in our equipment maintenance dashboard, we are calling out to the containerized AI services or cognitive services. In this case, we have both anomaly detection as well as the text analytics. So we have, once the maintenance engineer is at the site, so there is sensor data, there's a numerical time series data that's coming from the site. There's also the log data, and all of this gets ingested into our TIBCO Spotfire platform. And then we call these anomaly detection and the text analytics routine through our Python data function feature, and then seamlessly develop these visuals, which involves clustering the anomalies in specific time windows, identifying the key driving factors, assigning specific fingerprints, and then finally relating to text fields. And then once we have that, we then alert the case manager, and obviously a further extension to this could be how we alert it through emails or texts, example. So without further ado, I'm actually now going to go right into our demo, see how all of this is in action. So here, this is a phase one, and this is where the central data science team sits. The analysts log into the TIBCO data science platform, a neat platform where the first logging in, we see we have concept of workspaces, the work files, and the people. Just looking down, you can also see just some of the most active workspaces across the time span. And if you just scroll down, we can just see some of the recent activities. And we have to remember that workspaces, so I'll get into concept of workspaces, which involves a working group, the team that works on a specific project. And this would involve work files being embedded in workspaces. So let's get into this. We also have the feature where you can just search the workspaces by the members, by the name itself, or just by the name of the workspace. So in our case, let's search by anomaly detection, and right here we can see, so this is the workspace. And right, looking at this workspace, this first just gives us an overview of the work that's been happening. A data scientist can build a workflow, and then you can have other analysts who can come in, change some of the parts of the workflows. And all of this is very neatly versioned inside this platform. And we can just see the updates along the way. Just on the right side, we also have the ability to even add notes. You could even add additional members to this workspace, or even edit the permissions to what they can do with this workspace. So now getting into the work files, let's get straight into, and work files is where you have the workflows being stored. You could also even have some sample data, or if we have a data scientist who decides to write code through our notebook capabilities, you could have the notebooks embedded into this workspace, and finally into the workflow itself. So I'm going to go ahead and open this workflow. And there you go. So just the first look at this. So on the left-hand side, we have two tabs, which are the operators. And you can see we have a wide range of operators going all the way from loading of the data to exploration, transformation, and multiple modeling operators. And these are very simple drag and drop operators that we can connect in a workflow to basically with little to no code required. And in our case, so this is our data, and we could just actually go ahead and just quickly run this. And we can see that the flow is over. And this right here gives, we can click on these individual operators to see output at every stages. So this is our input data. So here, what we have is a timestamp, and then we have various sensors here. The one we are interested in looking at or detecting anomalies on is production per minute. And you have other sensors as well. You have pressure, barometric pressure, and you have a bunch of differential pressure sensors as well. Now we go through a series of transformation and filtering on the data. We transform the timestamp We get rid of some of the features that's not required, add additional features. And finally, we call out to the Azure ML service, to the anomaly detection routine in specific, to detect anomalies at a record level here. So if we just scroll to the right, now what we see here is this is the output. So I'm going to get into this in a little bit more detail. So you have the upper margins and the lower margins. Basically, for every given point in this AI-based anomaly detection system, it generates two margins and also generates what it expects the value to be. And depending on that, it basically tags whether this record is an anomaly or not. So and this is and we can see that we have to remember here in this at this phase, this data is very large and we're getting data from all the sites. So at this point, pretty much we have scored the data on across all the sites. And the next step we do really is to just export this data into a Spotfire binary data format, which would enable the maintenance engineer to faster load and process the data at the site. Now, at this point, the maintenance engineer has this artifact, and the engineer gets a call from this remote site, and this site really does not have really a good internet connectivity. So they get a call from the site supervisor to come down to the physical site itself to analyze the local site data and detect anomalies. And this is where we go on to the next phase, which is phase 2. And once the maintenance engineer arrives at the site, so he or she then pulls up this equipment maintenance dashboard, and this part here in the top left enables the site supervisor to give their inputs. So in this case, what's the metric that we're interested in detecting anomalies on? And we can select anything, but let's say for the demo here, we're going to select production per minute. We also have the granularity level that we can select. So in this case, it's by minute. And let's go ahead and detect anomalies. So what's really happening in the back end here is that once we click on that button, through our Python data function feature in Spotfire, we make a call to the container, and this is a REST call. We get the data back as a JSON. It's post-processed again, and then being displayed as these visuals. So on the top visual, we can see on the x-axis, we have the time, and on the y, we've plotted the original and the expected values. So original values in blue are the values that are coming from the site itself. And the values in orange or yellow are is the output from the model, or is what the model is expecting. We can see that the model is doing a pretty decent job here. And the bottom graph is really just the extension of the top graph. And what it's doing is it is just plotting the difference between the original and the expected value over that time. And these red markers are what's being detected as anomalies by the anomaly detection containerized service. So now we've gone from detecting anomalies. Now we're kind of seeing these clusters of anomalies. So at this point, the site supervisor might say, I'm actually interested in looking at a window of these anomalies, and they might be interested in further inspecting that. So we'll go ahead and select a time frame just leading up to these anomalies. And once we select that, we can now drill a level deeper to understand what was driving the anomalies in production per minute. So, and this should just take a few seconds. All right. Okay. So, and this is where, and a few things happening here. I'm going to get into details on the bottom, starting from the bottom left. So these are the key driving factors, or what were the key driving factors in production per minute, or the anomalies in production per minute in that specific time window, the time window we've selected here. And right off the bat, we can see here you have the barometric pressure sensor, the one differential pressure, and the waste gas sensor. So all of these seem to be contributing to the anomalies in production per minute, with barrel pressure being the highest. Now, now we've dug a level deeper. Now we know what's causing this, but we really want to be able to relate to other data sources. We have the log files that we can look at and try and see if what we are seeing in this key driving factors relates to what we see in the logs. And this is where we dig another level deeper to understand some of the maintenance work that was carried out prior to when we started seeing these anomalies. And this is where we call out to the text analytics container, where it actually, the input is just these long text logs, and it just breaks them down into key phrases. So by clicking on this Get Insights button, we see a few things happening here. So on the top right, now we see the time window, which we selected on the previous page. And on the y-axis, it's the metric that we are interested in detecting anomalies and learning more about, which is production per minute. You can also see that these were some of these maintenance actions that were carried out around that period of time. So, and what we see here in this little chart is just some more condensed view, which says, what were the actions taken by these engineers? And right off the bat, we can see that out of the 6 engineers who inspected this barrel pressure meter or barrel pressure sensor, 5 of them actually found some faulty readings or some faulty valve. And the first thing they did, which was according to the manual, was to restart the unit or restart the sensor. And it seemed to have worked. It seemed to have worked in this case, but what they did not realize that this was a very temporary fix. We also had one engineer who actually looked at this problem and said that this is a temporary fix and we would require a replacement of the sensor, before a breakdown occurs. And that's exactly what happens here. And we can see that the correct action to be taken was to actually replace this and not continuously restart this. And in a scenario where you don't have, where we don't analyze these log files, you would really require the maintenance staff to go over hundreds and thousands of lines of logs to actually point to the culprit. So right through this, we can really understand what the problem was. And at the bottom, there is this recommendation that we give out, which is, there's a complaint of this sensor, and we advise to replace immediately. The bottom, at the bottom here, where we can see the barrel pressure sensor over time, it's also the distribution of these key driving factors over that period of time. So this is for barrel pressure, but we can conveniently toggle to other sensors, and we can, and the site supervisor or the maintenance crew can get a deeper understanding of what the distribution of these sensors were around that time. So I'm gonna go back. So what we just saw really was how we went from collecting and processing this massive data from all the sites through our visually backed data science product, which is TIBCO Data Science. We score all of that data, and that serves as an artifact. And then you have the maintenance engineer who goes onto the site, and we go from collecting the data at the site itself to detecting the anomalies, finding a root cause, to finally recommending a corrective action, all at the site itself without the need of an active internet connection. And obviously, as just to echo what Michael said, we will be posting more resources on how we brought this demo into action. You could definitely look out for a recording that we did during our Microsoft build session and several other blogs. So yeah, so I'm just gonna go ahead and hand this. If there are no further questions, if there are, more than happy to answer them right now. If there are none, I'll be more than happy to hand the share over to Catalina.
Perfect. I think we do have a couple of questions. Kelly, I am seeing a couple. I see one. So how do we identify the key driving factors? Is this obtained from the anomaly detection routine?
Well, that's a great question. And actually, no, it's not. So the anomaly detection routine that we have from the containerized service, it's a univariate anomaly detection routine, meaning the input to that routine is really just a timestamp and one sensor value. And while that's great, there's also a limitation that you cannot really see if production per minute has correlation to any other sensor. So the answer to that is no. And we do this through, so what we do here is once we detect the anomalies, we train a random forest model to basically obtain the feature importances, which is what you see right here. And that helps us correlate to what was driving the anomalies in production per minute. And this is all achieved through the Python data function feature embedded in TIBCO Spotfire.
Mm-hmm. And just to add on to that, the way that works is we actually set up a 0-1 variable for when there's an anomaly gets a 1, and when there's not gets a 0. And the random forest model is a classification model that figures out what are the variables that are affecting the classification into the 0 non-anomaly or the 1 anomaly. And that's where those key driving factors are the variable importances from that random forest model. So that happens behind the scenes. And that's another example of how, this pluggable architecture. So that's something we set up and run through, a Python call in TIBCO Spotfire Python service. That's whereas the Microsoft pieces that we're using here are pre-trained cognitive services models for doing the basic detection univariate, as well as the cognitive services explanation. And interspersed in all of that is this multivariate TIBCO anomaly detection model through the random forest. Perfect. We have another question here about what services are required for accomplishing the anomaly detection. So this is a combination, as we mentioned here, between Microsoft and TIBCO. So if you have Azure, we can help you, and you have Spotfire, we can help you wire this up. Otherwise, you would need to be able to access those two technology pieces. And if you don't have Spotfire, we can help you get that. And if you don't have Azure, we can run it all in Spotfire. So lots of options here. So yeah, whoever's asking that question, feel free to send us an email and we'll follow up with you.
That's awesome. And I think we have one last one. I think, Diva, you can quickly show how you are calling the Microsoft Anomaly Detection Service in Team Studio. I know we have a node, and if you can just show that to Oliver.
Yes. All right. So what we've developed here is, so this is a custom mod, and we have a very comprehensive development kit that you could use to conveniently develop these operators. We have a series of operators, but you can always feel free to develop more for yourself. So what it does is really in the back end, when we run this, so we select the timestamp column from the data set. We also select the response column, what we're interested in detecting anomalies on. And here is where you enter your credential, or I would say the URL or the credentials that you receive from Microsoft. And there's a few parameters that we've also enabled in this, things like sensitivity levels. What it really does, it tells you what is the confidence of your of the anomalies detected. And this is a value that goes between 0 to 100. You also have maximum anomaly ratio is, let's say, given 100 points that you are looking to analyze, what's the maximum anomalies that you want to detect in that? And obviously, one of the most important features is also timestamp granularity, as we know that in time series data, the data coming off from sensors can be at different granularities. And what we do is that we just we just hook this up, and once we run this on the input data, you get your output values, which is these 6 columns that we're seeing here.
Mm-hmm.
Does that answer the question?
Yeah, and I will follow that with what Michael said. Any additional questions, we'll be more than happy to understand the behind the scenes and help you wire up the use case.
Mm-hmm.